Rehearsing? Rehearsing what?
Our musical.
Musical? What the musical is about?
It's a surprise
For whom?
for you.
I'm already surprised.
Oh, good.
Here is the link just in case, because we need to. And I think you all are like co-hosts of the stuff, so you'll be admitted as we go, right? If you decide to join. Oh, and I can put focus camera on everyone anyway. It's nice to see you. So, how many ways to predict future do you know? Three. Today you have four. Four. Right. Schroedinger had his friend and competitor who designed alternative version of the quantum theory. The name is Werner HEisenberg, and it's on one hand more complicated and another more practical. It's just a little, and the third it is more sophisticated, so that it's not included in the minimal core of the theory. So I try my best not to lie, but in fact, there was a little deceptive point in our previous studies. We decided that filtering free space is a simplest model, right? And we decided to chop our scientific interest on two parts. One, whether it will shrink or expand, and by now we know it expands and it gives us uncertainty relation. Right? And James, I'm not the last. And James did a movie how it expands, right? The second one, the first, another part, is called the center of the wave packet is doing, right? Hypothetically, we will go according to the first rule of unity on the line with a constant velocity, but we do not know for sure. It can be proved by the method that we covered by initial condition, blah blah blah, right? But it is a waste of time, and if we use different method to answer about where the center is going, you'll get a chance to learn new fun stuff. Well, fun from the point of view of theory. If you hate math, it will be no fun at all. Yes. Yeah. So B, who was presenting postulate number 4, right? Huh? The first one? No, the second last was the last one. The A in the angular brackets. No? Anyone? But we were discussing it multiple times. If we do know wave function, we can find the expectation value of an observable that is described by an arbitrary operator A. I think A stands for arbitrary, right? Right? So we just make a sandwich between wave function, operator, and another wave function. Integrate and get the results that will predict outcome of an experiment. Okay? So the idea of Heisenberg is that why next generations of undergraduate students should waste time of computing wave function if no one knows what it is? Can we do the same way as in classical mechanics? If we need just expectation value of operator, why don't we write a differential equation for this expectation value? and solve it like one line, two lines, instead of it, just omitting wave function from explicit consideration totally. Okay. It's a great idea. It just is not, it will not work all the time, but in some problems, it will be more profitable, more quicker, less expensive than Schrodinger equation. By learning force way to predict future with theorem involved, right? Okay, so there is a very simple and elegant derivation that one can do on the board without a computer within 15 minutes. I don't know why I'm planning to waste 30 minutes on it. Maybe because I'm ready to write and the slides are already ready. But here is the idea what we are going to do. So we will first do the preparational, and second, we will follow expectation value in angular brackets. Expectation values in angular brackets does have two wave functions, one regular wave function, another conjugated wave function. You are following? Not a surprise. And the function regular wave function obey which equation? How does one find solution for a function? Schrodinger equation, right? But one of the wave functions that we are going to look at is conjugated, is transposed. Another thing that we need to look how the expectation value will change over time. If you want to find how something is changing over time, we are exploring its time derivative. Okay. I told everything. We are basically done. The rest is converted into math. So we will try to derive what happens if you get time derivative of this expectation value. Right? We will attempt to connect it to expectation value without time derivative and get probably first order differential equation. Right? Support? No one is in doubt. Why? Okay. I was scared, like my heart dumped to the feet. Why? So time derivative of wave function comes from Schrodinger equation, but we need time derivative of the conjugated wave function. And in brief, if you just talk without equations, conjugated wave function propagates backwards in time. It's like a time machine. And it is a slightly different Schrodinger equation. So we need Schrodinger equation forwards, Schrodinger equation backwards, plug them into there and see what happens. And as the result, we hope to get an equation of motion for expectation value, and we are going to apply it to center of the electron in free space to discover that it will move on a straight trajectory. Okay. Our system is ready. Probably we will not use it, but I'm happy to see that the equipment is working. Okay. So there are a couple of slides reminding the homework which is due.
Recording in progress.
Good. Oh, okay. There are two microphones and two speakers. It's we can talk like. If you do you hear me? So there were a couple of slides with homework, which is due on coming Wednesday. Please try your best to bring. You already know the routine procedure how we will do, but it's not a major intellectual challenge, but it needs time. Start it earlier than the hour before the meeting. Hopefully, some of you have already started. Slide right after the homework. What do you see? Those who are on Zoom do see directly. Those who just look on the slides can just describe by your own words. And I do this little challenge thing so that we keep interactive atmosphere and no one falls asleep. What do you see right after the homework reminder?
Heisenberg
Uh-huh.
equation of motion.
Okay. But what else do you see? Other pictures?
Pictures of Heisenberg.
What is he doing? Not only, no. Look.
Looking at the
Picking
momentum.
petals off the left flower.
Yes. And how do you call this activity? Luck? Any other? Like loves me not?
Oh, yeah.
Right? So he's trying to get an answer on the unpredictable question by predictable procedure, right? And this is not just a caricature, it is one of the post stamps from Germany. A few lectures ago, we looked on the German money, now we look on German post stamps. So they're proud of Heisenberg, who was like native German, and they make a laughter of him. That he is father of uncertainty, and he is like uncertain to predict position. You see, there is like call outs, words out his mouth. Okay. So this caricature shows him in his sunset time, and on the right there is a younger, which is about your age when he designed the stuff. On the bottom there is an uncertainty principle, and on the someone is German. And on the top there is a Heisenberg equation of motion that we need to get into by the end of the meeting, within whatever minutes. Whatever we need. So what do you see 2 slides later?
The permission conjugation
For what?
for the time-dependent Schroedinger equation.
Yes, but why there are 2 of them?
I don't know. One for the normal one and one for the conjugated.
Yes.
Forward, backward.
Yes. Forwards and backwards in time. And do you see any differences? What comes to your attention? Are they completely identical, or there is any difference?
Well, the size has a star. That's been conjugated. And the Hamiltonian matrix switch positions with the psi. One gives the calling values while the other gets the row values.
How perfect it is. I was always confident that you can teach this class without me. One just needs a little like plan. You do. Of course. And they do not need to do anything. It's already showing the stuff. So the wave function and the Hamiltonian operator are swapped by their order, right? That's it. That's 50% of our success. We have 50% done for sure. If you are not confident, if you're not comfortable with this. Oh, yes, and it is final outcome that was on the was stem from Germany, right? Forced way to predict future. Okay, so here is the whatever force of fifth postulate, the way, the bridge between abstract wave function and results of experiment, right? So conjugated with a sandwich. Then we do need to get the time dependence of this stuff. And transpose means transpose here, Hermitian conjugate, transpose, and complex conjugate. So now for about 10 slides, I will be going around the same idea which you already got. So if we do have Hermitian conjugate of the operator times wave function, and under operator we may think a matrix, and under wave function a column vector, right? So if you apply this conjugation, then one should be able to prove that result will be equal to conjugated operator and conjugated wave function. But it will be row instead of column, right? And this one will be Hermitian conjugate. So should we prove it? Can we believe it? Well, the result of conjugation should be row vector, right? You can believe it. The result of row by matrix should be again row vector. So at least by dimensions, it agrees. So it's not a proof, but it is a demonstration that it is not a nonsense. Again, not as a proof, but just as a convincing argument. So matrix times column should give the same result as column times matrix. And if one would make an experiment and check it element by element, one would see that it is correct. Please. This looks okay for you. If anyone wants to object, if any. You don't like this sticks and bars? You agree or you object? Not object. Oh, it's same story as white. If any, do you approve? Do you agree? Okay. So I will take as you accepted this little manipulation of making Hermitian conjugate of the matrix by vector. Now, what, and it is our own new friends from 2 slides ago. Sign column is for wave function, and square matrix is for the Hamiltonian operator. Now, if we apply Hermitian conjugation to left and right, on the right we will have what we agreed on, right? Swap of the order and conjugated row, and Hamiltonian under Hermitian conjugation doesn't change. If it is real and has only diagonal elements, we can agree on this. If it is not, we would request a proof, but right now instructor invites you to believe. And here time derivative is not related to this conjugation or matrix transpose, so it's just time derivative of this pink row vector, right? So those are players, those are units, components that we'll plug into our overarching result for predicting future for selected expectation value. Okay. So basically, we will take this one and plug them into time derivative of the stuff that goes over time derivative of the expectation value, right? Okay. And here is the same thing, just in a more mathematical way. It's very unusual and unexpected they swap the order, but it is a key factor of all this little story. Okay, so we need to arrive to this equation, to HEi equation. So for regular wave function, Hamiltonian acts from left to the right. For conjugated, it acts from right to left. It just acts in the opposite direction, right? Because matrix changes wave function, but it is written at the right side. So we can symbolically think that it just acts backwards, which was confusing me a lot at the undergraduate times. I thought the instructor is insane. Like in the linear algebra, it's always operator acts from left to right, and then someone tells it goes backwards. It mathematically it is seen, but it sounds awkward, but it is what it is. Now, forwards, backwards. Difference is also in a sign. Do you see it? So the sign is changed because of the conjugation. And if you would solve, this is not solution, this is just a little demonstration. If you would solve, it would evolve in time with evolution operator, accumulation phase, minus, and then forwards in time. Here, if you swap sign, it means we can think of accumulating phase backwards in time. It's all symbolic, but without this provoking verbalization, the information will be wiped off the brain in 5 minutes after the class is ended. And now someone asked, what were you doing? Oh, we were propagating backwards in time. So here is the main slide of the today's meeting. If you were disfocused or just taking your time to relax before, or you plan to do it after, it's fine. It's only the one we need to concentrate on. So the top line is the just standard way of making quantum sandwich to predict outcome of measurement for certain observable. And we do see that there is regular wave function and backwards wave function. Now, if we will set time derivative, the time derivative and integration can be swapped because they act on the two different domains of variables. And then if you apply time derivative to a product of three functions, how do you call it? Product rule, right? So derivative of first, second, and third unchanged. First unchanged, last unchanged, derivative of the middle one. First and second unchanged, derivative of the last one. Approve? Agree? Thank you. The derivative of the operator in the explicit form is very interesting, but very rare. And for until the end of the class, we basically do not need it, so we can set it to 0. But if eventually we need it, we can bring it back. So this happens if we want to model lasers that irradiate our models, right? Then something is Hamiltonian is time dependent. But if you do not have external perturbation, we are fine with only the first and last term. And now you see we do have time derivative of the conjugated wave function and time derivative of the column of the regular wave function. Where do we take them? So where can we take this time derivatives? It's not a challenging question. It's you don't need to be a brilliant STEM researcher. One can use just linguistics and logic. Right. Information is expected to be delivered in a consecutive order, if it is not a made up trap. And if something is used, it probably what was delivered like a couple of slides before. So where do we take time derivatives all the way function from?
Do we plug in the stuff that we derived earlier? The derivative of the conjugate also.
Perfect. It's a perfect answer, and I am confident. I know that Kaiden knows what he's doing and saying. But even if we would bring here a history major, we just sit attentive. He or she could answer the same words, and you are absolutely correct. So, where do we take this component? We take what we derived 2 slides ago, right? So. And what did we derive 2 slides ago?
We showed how the conjugation affects the order of Hamilton.
Right. We take Schrödinger equation, and on the left side you have time derivative. On the right you have combination of Hamiltonian and wave function. Right. We want to replace time derivative with combination of Hamiltonian and wave function. Doable, reasonable. Comments. Otherwise, this one will not be cool. It's original. Okay. So following the instructions from Kaiden, replacing regular wave function by regular Schrödinger equation minus constants operator times function in this inverted plus, and then wave function Hamiltonian. So we are getting a combination, and it is maybe the second most important slide. The writing here doesn't surprise you, right? You see naturally following from the previous one. So this stuff comes from the derivative from the Schrödinger equation, and this stuff comes from the Schrödinger equation. Now the constants can be moved to the front. Integration stays here, and then let's focus with moderate level of sobriety. What is similar in each of the terms? Again, it's you do not need to be STEM brilliant researchers. Just looking on like symbols, one can be graphical designer or language editor. Like how this combination of symbols similar and different from this one. What does it start from? What does this start from? What does this ends with? What does it ends with? So can we just follow blue and red lines and put 2 things outside of brackets? Right? So we take psi star out of brackets from the left and psi without star outside of brackets from the right. What do we see? Haha. Right? Ha. So we already learned in the past. I think it was presentation of Ifeani in our first session, commutation, right? So the commutation is a critical part of the Heisenberg vision of quantum theory. So one cannot swap order of quantum objects in mass liberally. The order matters. And since an outcome depends on this ordered thing, it's definitely likely not to be equal zero. It's subtracting them after swapping should give different thing. Let's look on it from the other aspect. I will not rename it, but what if we would rename it and tell it like maybe O operator? This looks like a protocol to find an expectation value of an O operator, where O is equals DDT. Sorry for my perfect with sign minus calligraphy. So it looks like we are sandwiching not the arbiter operator A, but combination of Hamiltonian A minus A Hamiltonian, right? But the rest looks like a sandwich. And it is new operator O. You see it. Right? I don't know what to say next. It's basically done. I'm curious to look on the next slide, but we can replace this sandwich symbol by angular brackets. And then we will see the stuff that we need. So the expectation values are these angular brackets are equivalent with taking integral and multiplying by conjugated from the left and non-conjugated from the right. Yes. So at the additional rectangular brackets may surprise you, right? Because no one defines it before, or maybe we define it while talking about commutation. So quantum mechanics was created by lazy people who do not like to write many symbols. They failed this time because if one count each symbol, it is equivalent. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. But by some reason, it is common notation to rectangular, maybe it's safe space. Rectangular brackets symbolize swapping the order and subtracting. So rectangular brackets stand for commutation. And then time evolution of the expectation value of an observable is equal to expectation value of commutation of that operator of that observable with operator of total energy. This is a little simplification to be closer to the real life. When Heisenberg was thinking about it and deriving it, he wasn't putting angular brackets and expectation value. He was just telling that time evolution of operator equals to commutation of that operator with Hamiltonian. And then anyone who wanted to follow him, he thought like, okay, operator is a matrix with so many elements, write down each element and equation for each element, which of course was not happily acceptable by community, and community decided to go to Schroedinger, we didn't require everyone to follow each element as function of time. But if we put expectation values, then it is something hypothetically doable. And in our practical question of time evolution of the center of the Gaussian wave packet, it will be very much applicable. The time that we have now is not allowing me to go through this interesting and pleasant journey, but I am confident we will be able to complete it next time. Here is a little of my life experience. I have got a B grade for the class I'm instructing right now, because I didn't answer on the oral exam the question that is short right now. I did answer, but not in the crispy correct language form. So if you do see that the operator A commutes with Hamiltonian, commutes means commutation equals 0, right? Then the expectation value of that operator will not change over time. Solution of that differential equation, right, will give a solution that expectation value at time t will be equals to expectation value at time 0. So in case operator commutes with Hamiltonian, then expectation value doesn't change over time, it is conserved. So one can derive conservation laws, conservation of momentum, energy, angular momentum in this way. And my error that I got overgraded answered, an operator should commute, for example, with Hamiltonian. The instructor started, what do you mean, for example? It's only with Hamiltonian. Go away, you get beat. Okay, and anticipate that it's enough for today. So I'm returning 3 minutes of your time that I either was borrowing in the past or will borrow in the future. Meeting is done. Everyone is welcome to depart and disconnect. Looking forward to see you and your homeworks on Wednesday. And I'll stay here to answer any questions if needed.